Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on November 25th, 2025, about 3 days ago. This paper introduces a way to edit how objects and cameras move in existing videos by tweaking just a handful of motion points, and in human studies it was preferred about 70% of the time over previous video editing methods. The paper is titled MotionV2V, Editing Motion in a Video, and as we will see later, the results open up some surprisingly intuitive tools for reshaping motion without breaking the original scene. So after that high-level setup, Figure 1 lays out how motion edits actually work and what kinds of edits they enable. The top left pipeline panel shows an input video plus source tracks and user-drawn target tracks being fed into a diffusion model to produce an output video that follows the new motion. The top right application panel illustrates alternate outcomes, where the same dogs race but different winners are created by tweaking their trajectories. Along the bottom, 3 panels show moving objects, changing the camera path around a swan, and retiming a car and truck so that their speeds swap while the city scene stays consistent. Alright, Figure 2 gives concrete examples of what those motion edits actually do in full videos. The top row shows input clips and tracked points, while the bottom row shows edited outputs that follow the modified trajectories. On the left, the cat gradually moves away from the bowl, yet the fish and background stay consistent because only the cat's path changes. In the middle, camera control repositions and zooms the view over the swans while preserving the same underlying scene. On the right, time control delays the duck's appearance, so the same frame index can show entirely different content. While Figure 4 explains how the training pairs for motion editing are created. The full reel video at the top is first clipped into a shorter reel target video, which preserves natural appearance and motion. A video diffusion model then generates a motion counterfactual version, with prompts like make him twirl plus temporal and spatial augmentations. Crucially, shared points in the first and last frames anchor tracking, so trajectories align across both videos. Figure 5 shifts from data creation to the actual editing engine, showing how motion conditioning slots into the diffusion backbone. The left side stacks the counterfactual video and both sets of tracks, which are encoded and merged by channel concatenation. The middle control branch duplicates the first 18 transformer blocks and injects motion signals through 0 initialized MLP layers. On the right, the denoising die-T produces an output video that preserves appearance while following the edited trajectories. So while Figure 5 described how the model is built, Table 1 reports how people actually felt about the edits. The table lists 3 questions about content, motion, and overall quality, and compares 4 methods side by side. Participants chose this method about 70% of the time for all 3 questions, while the strongest baseline, ATI, only reached about 25%. Revideo and GWTF barely registered, typically scoring under 5%, which highlights how much more convincing these motion edits appear to human viewers. So while Table 1 captured human preferences, Table 2 reports objective reconstruction accuracy across methods. The table lists 3 metrics: L2 error, structural similarity, and perceptual distance, comparing this approach with ATI, go with the flow, and revideo. Lower L2 and perceptual scores mean closer pixel and perceptual matches, while higher structural similarity means better structure preservation. This method wins on all 3 metrics, with roughly half the L2 error of ATI and clearly better perceptual fidelity. Alright, while Table 2 quantified accuracy, Figure 7 visually compares motion edits across 8 tough scenarios. Each row shows the input video, this method's output, and the ATI baseline, so viewers can judge whether motion changes stay consistent with the scene. Colored dots trace objects over time, revealing when baselines lose track or invent new content. The icon key strip at the bottom explains which edits involve moving objects, changing the camera, retiming events, or altering all frames. MotionV2V shows that directly editing sparse motion trajectories can reshape object and camera motion while keeping real scenes intact, and it clearly beats prior video editors in both human studies and metrics. Broader picture, it points toward intuitive, point-based control for future video tools. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.